Now that we have understood what tensors are in the last video, it's time to understand how tensor works in PyTorch, what different functions and computations we can perform on tensors, and what manipulations we can do in tensors data, and what are the different available functions in tensors or in PyTorch for us to use. So let's get started with that. So I have this Jupyter Hub notebook with me. First thing I'm going to do is create a new notebook, and I'm going to name this PyTorch Tensor Masterclass. PyTorch Tensors masterclass.ipynb. First thing first, we have to import torch. So I'm going to say import torch. And because we will be needing numpy arrays as well, so I'm going to say import numpy as np. Now that we have torch imported, the next thing we should always do is check for the CUDA. So I'm going to say torch.cuda.as available, and I should see true. So that means my CUDA device is available for PyTorch to use. Now let's start with the function. The very first function that we'll understand is torch.tensor. So this tensor function, or this torch.tensor function, is used to create tensor directly from Python data. Python data can be list or tuples, and we can directly create torch tensor from those Python data. What I mean is, let me create a data. That means a Python list. I'm going to create a 2D list. So 1, 2, 3, and then I can say 4, 5, 6, 5, 6. So this is my data. And this should be comma. Now I can say x data equals to torch dot tensor, and I can pass this data. If I have a look at x data, so this is now my tensor. So it's not Python native data type anymore. It's the PyTorch tensor. Now let's move to another function, which is torch.fromNumpy. So this function, as the name suggests, is used to create tensor from the NumPy arrays. So I'm going to create a NumPy array, which I'm going to call NumPy array equals to np.array. And similarly, I can create a list of 7, 8. Should be this. And here I can see it's a 8, 9. And I can say x underscore np. That means I'm creating a tensor. So the function for that is torch dot from numpy. And I'm going to pass this numpy array to this torch dot from numpy. And if I have a look at x np, I'll get another tensor. So this is not a numpy anymore. This is very useful when you want to create tensor directly from numpy array. So you don't have to do any other manipulations or configurations. You can just directly use this function, pass your numpy array, and there you go. You have your tensors now. Now the another function we'll see is torch.zeros. Torch.zeros. Zeros. So torch.zeros function creates a tensor filled with all 0 values. So all you have to do is specify the shape. So you can say here's a 3 by 3 matrix of zeros. So these kind of functions, or especially the zero function, is very useful when you're initializing your weights, or if you want to have a matrix as a placeholder before training models. So how to create is x zeros equals to torch dot zeros, and all you have to do is give the shape. Should be x zeros. And there you go. You have the matrix of 3 by 3 with all the zeros filled in. Now, before moving on, let me explain that every tensor has a shape which tells how many elements are there in each dimension. So for example, this tensor has 2 rows, 3 columns. The shape helps PyTorch understand how to perform matrix operations like addition, dot product, multiplication, etc. So you can think of shape as the tensor's blueprint, how data is arranged within the PyTorch memory. Now let's move to another function, which is torch.rand. So this function returns a tensor filled with random numbers between 0 and 1. And it's a uniform distribution. So each time you run it, you'll get different numbers. It's widely used for weight initialization or testing random data during experiments. How to create one is I'm going to create a variable xrand torch.rand, and I can give the shape. And then if I have a look at it, and there you go, you have your tensor filled with random numbers between 0 and 1 with a uniform distribution. Next function will be torch.ones. And you all might have guessed by now, this tensor is used to create a tensor filled with all ones. This function is perfect for testing operations like addition and scaling, because since multiplying by 1 keeps value unchanged, so there's no point of using that. So let's see how to create tensor of ones. I'm going to name x ones equals to torch dot ones, and all you have to give is the shape. And then if you look at this tensor, it's the tensor of shape 2 by 3 filled with all ones. And let's say you want to move this tensor to the GPU device or the CUDA device. You can specify the argument here, device equals to CUDA, and there you go. So you'll see this argument that your tensor lives on the GPU memory as of now. Similarly, you can save CPU instead, and there you go. Your GPU, or sorry, your tensor is in the CPU memory now. So the next function will be torch.arrange or arrange. Now let me just write this function and then I'll explain what this means. This should be arrange equals to torch.arrange or arrange. I'm going to say 0, 10, 2. And let's print. So how this torch.arrange or arrange works is it creates evenly spaced values within the range you have specified. So in this case, it's 0, 10. So this works exactly like Python range function. So if you look here, what I'm saying is starting value is 0 and it ends before 10. And every time you should increase the next value by 2. What you should see in the output is 0, 2, 4, 6, 8, and 10 is not included in that. So there you go. You have evenly spaced out tensor using arrange function. Now, similar to arrange, we have another function called linspace. So torch.linspace. Let me just write this function. Linspace equals to torch.linspace. And I'm going to say 0, 1, you have to define argument called steps equals to 5. Then we can print x linspace. So how this works is this function also creates evenly spaced values between 2 points. But in this case, both the points are included. Whereas in arrange, the last point or the end point is not included. So in our arrange function, point 10 is not included. Whereas in linspace, 1 and 0, both are included in that evenly spaced values. So this is really useful when you're creating smooth intervals. So for example, when you're plotting curves or calculating or creating gradients, especially. What gradients is, we'll understand in the future videos, but for now, we have this utility function provided by PyTorch. So if I see the output, you'll see the evenly distributed output, and both the ends 0 and 1 are included in the response or the output. Next, we have torch.I function, torch.I. Now, this function is used to create identity matrix. So identity matrix is a square with ones on the diagonals and 0 everywhere else on the matrix. So this is heavily used in linear algebra, matrix multiplication, and deep learning. Like when you're normalizing vectors or keeping weights orthogonal or 90 degrees. So how to create one is I'm going to create a variable called xi and torch.I, and then all you have to do is the shape, and then you can say xi, and there you go. So you have your matrix 4 by 4 filled with ones on the diagonal and 0 everywhere else on the matrix. Now the next very important and somewhat complex function is torch.empty. So torch.empty is useful or is used to create a tensor when uninitialized values. So what I mean is when you do torch.empty, PyTorch does not initialize values in your tensor. So this torch.empty gets whatever arbitrary value was already there in that allocated space. So this is extremely useful. Now remember, torch.empty does not have zeros or random numbers. PyTorch does not initialize any values for torch.empty. It just gets the value, whatever value was there in that memory space before this tensor or empty tensor was even created. Now because of this, torch.empty is extremely optimized and fast function because PyTorch doesn't have to initialize value. It's just empty raw memory. How to create one is x empty, and you can say torch.empty and give the shape x empty. Now in this case, you see 0, 0, 0, but that does not mean PyTorch has initialized this tensor with 0 values. It just picked those 0 values because whatever space, whatever memory space this tensor was allocated to has or had this value. Now, if I run this again, for example, I'll see totally different values. Another function we're going to have a look is random int or rand int. And int, let's create this function. And int equals to torch dot rand int 0, 10 and 3 by 3 or 3 by 3. And if I look at x rand int, so how this function works is you have your low and high value and you give the shape. PyTorch will create a tensor with random integer between 0 included and 10 not included of 3 by 3 size. So that's what you see. All the matrices or all the values in the matrices is between 0 and 10, 0 included, 10 not included of size 3 by 3. This function can be really useful for testing or simulating labels or creating random indices. Now that we have learned about few of the many tensor functions, let's look at some of the operations we can perform on tensor itself or tensors itself. So very first thing we'll do is understand the add operation, which is basically adding two tensors and how addition works in the tensors. So I'm going to create two tensors from Python list. So I can say x equals to torch dot tensor, and I can give 1D list of Python. And let's create another torch dot tensor, and we can say 4, 5, 6. And let's do addition operation. So I'm going to say result equals to torch dot add x comma y. And let's look at the result. So you get 5, 7, 9. Now what you see is tensor is doing element wise addition. So 1 is added to 4, 2 is added to 5, and 3 is added to 6, and hence you get 5, 7, 9. Now similar to Python for performing element wise addition operation, you can use plus operation or plus symbol directly as well. So instead of doing torch.add, you could have also said x plus y, and you'll still get the same result, 5, 7, 9. Now here you have seen that shape of both x and y tensor is same. Both have 1 row and 3 columns. So it was easier to perform element-wise operation. But what if they are of different shapes? Then, similar to NumPy, Torch or PyTorch also supports broadcasting. So how does broadcasting works, or what broadcasting is? It allows PyTorch to create element-wise operations on tensors of different shape without actually creating the copy or different copy of the tensor. So let's have a look. at the example. So I'm going to create, or I'm just going to copy these two things, and let's make this a 2D array. So, and let's say 7, 8, 9. Now let's perform addition on this. So result if equals to x plus y, and let's have a look at result diff. So you see 5, 7, 9, 11, 13, 15. So how this works is, first, this was broadcasted in element-wise operation to this array. So 4 plus 1, 5, 5 plus 2, 7, 6 plus 3, 9. And then this was broadcasted to this array for operations. So you get 4 plus 7, 11, 5 plus 8, 13, and 6 plus 9, 15. So that's how PyTorch manage operations or element-wise addition on different shapes. Now let's have a look at torch.multiplication method or torch.mul. So I'm going to create two tensors again, torch.tensor, and let's create 1, 2, and 3, 4. Let's create another matrix or tensor, torch.tensor of 2, 0, and I can say 1, 3. And if I do result equals to torch.all, it's x, y, and then have a look at the result. Now it's 2, 0, and 3, 12. So that's what you get. So in this case, remember, PyTorch is performing element-wise multiplication and not the matrix multiplication. So this is just 2 times 1, you get 2, 0 times 2, you get 0, 1 times 3, you get 3, and 3 times 4, you get 12. And if you want to check the shape, this result has the property called shape. So shape is 2 by 2. The next function we'll understand is matmul, which is basically matrix multiplication. So I'm going to say torch.matmul. So let's create two tensors. I'm going to say A equals to torch.tensor. And let's create 1, 2, 3. And another one, 4, 5, 6. Let's create another tensor B, and let's say torch.tensor 1, 2, 3, 4, and 5, 6. First thing, let's look at the shape of each tensor. So let's say B dot shape. So this is 3, 2, and let's look at the shape of A. Shape. And this is 2, 3. Now let's do the matrix multiplication. We have a function available called torch.matmul, and all you have to do is pass in your tensor, then let's just print result, and there you go. Torch.matmul or matrix multiplication is same as the dot product in linear algebra. So each element of the result is sum of the row times column multiplication. Now, one of the biggest condition for matrix multiplication to work at their shape should match certain condition. So in this case, shape of the tensor A is 2, 3, and shape of tensor B is 3, 2. And when you're going to multiply it or have a matrix multiplication, the number of columns in the first tensor should match with number of rows in the second tensor. So here you see that my first tensor A, has a shape of 2, 3. That means it has 3 rows, or sorry, 3 columns. The tensor B has a shape 3, 2. That means it has 3 rows, and they both match. And the resultant tensor that you get from matrix multiplication of these two tensor is, or will be, 2 by 2. In this case, it's obviously 2 by 2. Now, how the multiplication is done is 1 is multiplied by 1 plus 2 times 3 plus 3 times 5, and you get 22. Similarly, 1 times 2 plus 2 times 4 plus 3 times 6, you get 28, and so on. And that's how matrix multiplication is done in PyTorch. It's very similar to the dot product. Now, there's another way to do matrix multiplication instead of using this matmul function is you can say result equals to A at B, and this will produce the same result. There you go. Now, this matrix multiplication is the heart of deep learning. It will be used in every neural network layer you will create. So make sure you understand. If you don't, just get the copy and pen and do these matrix multiplication manually instead of Python or PyTorch computing for you, and I'm sure you'll get it. The next very important function is torch.reshape, and we will be using this function a lot when creating our own network or deep learning models. So make sure you understand this. So for this, I'm going to create a single 1D array with a range function. And I'm going to say 1, 10. If you don't give the step, by default, it's of step 1. So let's see how our X looks like. So this is a straight tensor of 1 to 9 numbers. And then I'm going to create a reshaped tensor of 3 by 3 equals to X dot reshape. I can say 3, 3. And then let's see how our reshape tensor looks like. So reshape function changes the shape of the tensor without changing its data. So all the data you see in this tensor is exactly same as my 1D tensor or array. Now, the one very interesting fact or thing about reshape is it returns a view of the same data when possible. So this is efficient. What I mean by returning a view is reshaped function or reshape function does not actually create a copy or create a new tensor. It returns the view, or you can think of it as reshape function is giving you the imaginative answer of how this tensor will look like if it's 3, 3. So this is very memory efficient and optimized way of changing the shape of the function. And PyTorch is doing very good job with it. The next function we'll see is torch.view, which is very similar to the shape function. So this also returns a view of different shapes or how your tensor will look like in different dimension and shape. But the one important condition for this to work is the tensor should be contiguous in the memory. Contiguous simply means that the data or the values of the tensor are stored in continuous block of memory. Now, there are functions like narrow or transpose, which basically changes the structure of the data or structure of the values in the tensor. And these functions do not create the new copy of the tensor. Instead, they apply these functions in the existing tensor. So for view function to work, you have to make sure that your tensor is in the contiguous block of memory. You can check if if your tensor is in a contiguous block or no. So for example, you can say reshaped dot is contiguous, and this returns true. That means your tensor or this reshaped tensor is contiguous. But if I do, let's say reshaped equals to reshaped dot t, which is transpose, now if I check whether it's contiguous or not, contiguous, you'll see false. So that means transpose function has changed the structure and it's not in a contiguous block of memory anymore. Now, if you apply view right now, so you can say reshaped equals to reshaped dot view 3, 3 and view. And it should work as expected. You'll get the same response because we're just viewing the 3 by 3 shape of my arranged A-range matrix or A-range tensor. Now, I know this video is already a bit long, so I'll cover last two important functions, the squeeze and unsqueeze, and then we'll wrap up this video. There are many more functions as well, but of course we cannot cover it all in one video. So as we go through the series and if we are using those functions, we'll cover it as we go. But the second last function that I want to touch base with is the squeeze function. So that's torch dot squeeze. So how this function works, it removes the dimension or all the dimension of size 1 from the tensor's shape. So if you have a original tensor of shape 1 by 3 by 1 by 4, after squeeze, you'll get 3 by 4. So it does not do any data changes. It only changes the shape. So what I mean is, let's have a look. So I'm going to create a tensor x from the zeros. So I'm going to say torch.zeros. And let's get the shape of 1 by 3 by 4, 1 by 4. Let's look our original tensor. So this is what it looks like right now. And of course, it's a 0 tensor, so all the elements will be 0. Now you can see there are many extra dimensions that we don't even need. So what we can do is squeeze them. So I can say squeeze equals to torch dot squeeze, and then simply pass your tensor. Now if you look at the squeezed tensor, this is what it looks like. So the shape after squeeze is left as 3 by 4. So this is really useful and really great function for cleanup on the tensors after operations like model outputs or data loader batches that give extra singleton dimensions to your shape. Now there might be cases when you don't want to squeeze all the dimension or all the ones from the dimension. You can target specific by using x dot squeeze. And let's say I just want to remove the first one dimension. I can say 0, and this is what it looks like. So this function can be really handy when needed. And the last function we will be talking about in this video is torch.unsqueeze. So let's just write code and then I'll explain what's going on here. So I'm going to create torch.tensor. Let's create a tensor of 1, 2, 3, 4. And this is what my tensor looks like, a 1D tensor. Now let's do unsqueezed. Squeezed equals to torch dot unsqueeze, and then passing your tensor. Now this function take another argument called dimension. Now similar to squeeze, unsqueeze adds one more dimension or dimension of size 1 at the position you choose. So in this case, let's see what our shape is. So it's 4. Now I want to add another dimension to it. So I can pass x comma 0, which is the 0 is basically a dimension argument. And let's see what our unsqueezed tensor looks like. Oops, unsqueezed. So this function adds one more dimension to it. So similar to squeeze, unsqueeze adds up one more dimension. This is useful when you need tensor to match different tensor shapes. It could be because you're performing matrix multiplication or something, and you need matrix of the same shape. This function can be really useful in those kind of scenarios. Adding a batch dimension before feeding your data into the model, or expanding 1D tensor to align with 2D, 3D operations. So with that, we have now covered all of the essential PyTorch tensor creation and manipulation functions. And together, these functions will help you build your tensor foundation. Because remember, creating any model in PyTorch or understanding the code base or neural network, these tensors are really important, and you should be able to visualize them and understand what's actually going on. So with that, you just understand how tensors work and how some of the basic function within tensor works. I will commit this notebook in my GitHub repo with a lot more functions that you need. So make sure you use this notebook if you want to practice or just see how different function works. So with that, thank you so much for watching this video. And if you're liking this or if you're finding these videos helpful at all, please make sure to hit the like and subscribe button and share in case your friend needs these kinds of tutorials as well. And with that, I'll see you in the next video or next part of this series. And thank you so much for watching.